Let us now look at the simple harmonic motion when there is friction. We will begin again with the block with the mass m attached to a spring with a spring stiffness k. And we will place a coordinate system centered around the equilibrium position of the block. Let's say that at some instant the block is at a distance x from equilibrium and is moving toward that equilibrium with velocity v, drawn as a vector pointing to the left on the diagram. The elastic force of the spring is given by Hooke's law, F elastic is equal to minus kx. The friction on the block opposes the direction of its motion, and so it must point to the right. We will consider here a very simple case of frictional force that is directly proportional to the block's velocity. So we will write that F friction is equal to minus bv. Here v is the velocity of the block and b is a constant that accounts for the type of surfaces involved in the friction and possibly other parameters that might affect friction in general. Given that the velocity is the first derivative of the displacement with respect to time, we will actually write that F friction is equal to minus b dx dt. Now we can apply Newton's second law. The net force, in this case, equal to the spring force minus kx plus the frictional force minus b dx dt must be equal to ma or m d2x dt squared, as the acceleration a is the second derivative of the displacement with respect to time. Moving all the terms on the same side of the equation, we get for the equation of motion the mass of the block times the second derivative of the displacement plus the coefficient b times the first derivative of the displacement plus the spring stiffness k times the displacement function itself must equal to 0. This is a differential equation that we now must solve. But before we proceed any further with its solution, let's pause here for a little bit and look at the motion from the energy perspective. The mechanical energy is equal to the kinetic energy of the block, 1/2 mv squared, and the potential energy of the block spring system, 1/2 kx squared. In the absence of any friction, that mechanical energy will remain constant throughout the motion, only its form will be changing from kinetic to potential and back. We start with the block at the maximum displacement equal to a. Its kinetic energy there is 0 and its mechanical energy is entirely in the form of potential, 1/2 ka squared. When the block reaches the equilibrium position, the potential energy then will be 0 and the mechanical energy will be all in the form of kinetic, 1/2 mv max squared. Please note here that at that instant the block's velocity is at the maximum as well. After it passes the equilibrium, both the kinetic and potential energies are non-zero until the block reaches maximum displacement, this time on the other side, when the potential energy turns equal to 1/2 ka squared again, and the kinetic energy is 0. The block then begins to move in the opposite direction, passing through equilibrium, until it reaches its original position. The block has completed one cycle. The question now is, what happens in the presence of friction? We'll consider first small frictional losses, when the block oscillates but in a modified form compared to that in the absence of friction. In such a case, we see that the block is going back and forth with decreasing amplitude until after a while it stops at the equilibrium position. From the energy perspective, as the block moves back and forth, the friction converts mechanical energy into thermal until eventually all the mechanical energy is converted and no energy remains. If the frictional losses are sufficiently large, the block actually does not oscillate at all. As it begins to move, it will slide back until it reaches equilibrium and it will stop. The energy in this case decreases much more rapidly, and by the time the block has reached equilibrium for the first time, the mechanical energy has been dissipated completely. Now, as we have an idea of how the block moves, let's look at the equation of motion again. We will look for the solution of that equation to be of the form a constant a times e to the power of minus alpha t cosine of omega t plus phi. Here the displacement function is the product of two functions. One is the cosine that accounts for the possible oscillations, and the other is an exponent that modifies the amplitude by causing it to decrease asymptotically to zero. We will need the first and the second derivatives of that function. So the first derivative will have two terms. The first one, highlighted in blue, comes from the differentiation of the exponent function in the displacement. And the second one, highlighted in red, comes from the differentiation of the cosine function in the function for the displacement. Another differentiation, and the blue term from the first derivative, will give rise to two more terms, a cosine and a sine. And the red term in the first derivative will produce two more terms, a sine and a cosine. The second derivative will therefore consist of four terms. We'll highlight the cosine and the sine terms separately, the cosine terms in blue and the sine terms in red. The middle two terms in the second derivatives are identical, so we write them as 2 times alpha times omega times the expression highlighted in red. We also combine the first and the last term in the second derivative, both consisting of a cosine function, so that we get alpha squared minus omega squared times the expression highlighted in blue. Now what is left is to multiply the displacement function by k, the first derivative of it by b, and the second derivative of it by m, and add them all together. The total sum must equal 0. Let's rearrange all terms into two groups. The first will consist of all terms that multiply the expression that is highlighted in blue, a e to the power of minus alpha t cosine omega t plus phi. The other group will consist of all terms that multiply the expression highlighted in red, a e to the power of minus alpha t sine of omega t plus phi. The kx term in the equation has only a cosine part, so we have a plus k that goes into the cosine group. The b dx dt term in the equation of motion will contribute a plus b times minus alpha to the cosine group and a plus b times minus omega to the sine group. And finally, the second derivative term will contribute m times alpha squared minus omega squared term to the cosine group and m times 2 alpha omega in the sine group. We notice that the expression a e to the power of minus alpha t appears in every group, so we can actually cancel it. Now here, if we were solving this equation for t, we would normally move the second group of this equation to the right, so that we have an expression multiplied by the cosine function equal to a minus another expression multiplied by the sine function. The value of t for which the cosine function turns into 0 is not a solution to the equation, so we can safely assume that the cosine function is not 0 for our solution. Therefore, we can divide both sides of the equation by the cosine function, so that we get an equation for the tangent function. Then we can proceed to solve for t as having a value equal to an arctan of the ratio of the two expressions, and etc. The problem is that this solution is only for one particular time instant, and that is not what we wanted. We wanted a solution that works for any time. So we can't really solve for the time. This approach is not valid, and we need another approach. Let's go back to the equation before we started solving it. An expression times cosine plus another expression times sine must equal 0. This can be true regardless of the time instant t, only if both terms actually equal 0 simultaneously. That is, k plus b times minus alpha plus m times alpha squared minus omega squared times cosine of omega t plus phi is equal to 0. Here we can cancel the cosine omega t plus phi, so that we actually get k plus b times minus alpha plus m times alpha squared minus omega squared is equal to 0. At the same time, we have b times minus omega plus m times 2 alpha omega times sine of omega t plus phi. That also must be equal to 0. Again, cancelling the sine function, we get a second algebraic equation. So what we get is two algebraic equations that must be solved simultaneously. The first one is k plus b times minus alpha plus m alpha squared minus m omega squared equal to 0. And the second one is minus b omega plus m times 2 alpha omega equal to 0. After cancelling omega, the second equation gives us that alpha must be equal to b over 2m. With that value, we go to the first equation, and after a few more algebraic manipulations, we get that omega must be equal to square root of k over m minus b squared over 2m squared. Remember that k over m was actually equal to the square of the angular frequency of the block spring system in the absence of friction, here marked as omega naught, so that we can write for the angular frequency now with friction that is equal to the square root of omega naught squared minus b squared over 2m squared. So we have the solution of that equation of motion, and here is a brief summary of what we have got. Our results show that the function that we chose for the displacement is indeed the solution to the equation of motion if the coefficient alpha is equal to b over 2m, and the angular frequency omega is equal to the square root of omega naught squared minus b squared over 2m squared. Remember, omega naught was the frequency with which the system oscillates in the absence of friction. Its square is always equal to k over m. It is important also to note that we get the real value for omega only if the value under the radical is non-negative. In other words, we get oscillations only if the coefficient b is sufficiently small. That corresponds to the small frictional losses case in our energy analysis. In such cases, we talk about underdamping. If b is large, however, so that the value under the radical turns negative, there will be no real value for omega, and therefore there will be no oscillations. That case corresponds to the case of large frictional losses that we considered earlier in our energy analysis. We talk about overdamping. The critical case when omega naught squared is exactly equal to b squared over 2m squared leads to a simple exponential function for the displacement, that is a e to the power of minus alpha t.